Okay, what we're going to do today is we're going to focus on lesson 8.2 in the exponential and logarithms chapter. And we're going to focus specifically on the natural base e with two learning targets. The first being that you can use the natural base e to simplify expressions, and that you can use the natural base e in a real life context. Okay, and so before we really start to understand what E is, let's go ahead and just work through this activity below, and then we'll kind of develop an understanding as we go. Okay, so let's just recall some things about compound interest, okay? But what we're going to talk about today is continuously compounding interest. Okay, so we want to show that the frequency of compounding interest increases. The formula for compounding interest, A is equal to 1,000 times 1 plus r divided by n raised to the n times t power, approximates for the continuous formula, which can be done with a calculator. We're going to let p equal 1,000, r equals 6%. So since r is 6%, that means r for me is going to be 0.06. That's 6% as a decimal. And t for 10 years. And then, okay, so this is going to be for 10 years, okay, and we're going to compound it a different amount of times in a year. Okay, so let's go ahead and try the first one. Okay, so the first one says we want to compound quarterly, so we got to think about what quarterly means. So quarterly means that n is 4. It's going to compound 4 times in a year. Okay, so we know that the amount in my account is going to be equal to 1,000 times 1 plus 0.06 divided by n, which is 4, because that's the number of times compounded in a year. And to the n times t power, so n times t is 40. Okay, so we can just take our calculator out and do this. Okay, so let's crunch that number for us real quick. Okay, so we have 0.06 divided by 4 plus 1. Okay, that's this inside part here. Now we have to raise that to the 40th power. Okay, and then we're going to multiply it by the principal, which is 1,000. 181402. 1814.02. Okay, so if I have an account with a principal amount of $1,000 at 6% over 10 years, when it's all said and done, I'm going to have $1,814.02. Okay, let's do monthly. So monthly, we know n is going to be equal to 12 because that's how many months are in a year. So we can basically do the exact same thing here. We can say that the amount in my account is going to be $1,000 times 1 divided by, or 1 plus 0.06 divided by 12 to the, this will be the 120th power, right? Because 12n times t, 10, is 120. Okay, so let's go ahead and calculate that amount. So I'm going to go 0.06 and I'm going to divide it by 12. Okay, and we're going to add 1 to it, raise it to the 120th power, and then multiply it by 1,000. Okay, 181940. 181940. Okay, so let's just look at some differences here. So obviously we're making just a little bit more money over 5 years here. And that's just the difference between compounding my interest quarterly and monthly. So if you look here, you know, we kind of have like, this is like our first set here where we're making $1,814. This one's $1,819. And this, all we did was we increased the number of times that we are compounding in a month. Okay. All right. Okay, so then now as we move to the next one, we need to know how many months are in a year. or not how many months are in a year, how many weeks are in a year, which is going to be 52. Okay, so if I want to compound this weekly, I need to figure out how many weeks are in a year, which is 52. Okay, so we can go ahead and do the same thing. And as you can see, as we're working down through this, okay, we are finding out, as I just decide to compound it more frequently in a year, what's happening. Okay, so 0.06 divided by 52 plus 1 to the 520th power, and times 1,000. Okay, so as we can see here, it's increasing ever so slowly, but it is increasing, okay, daily. Okay, so as I increase the amount of times in a year, we can see it is steadily increasing. Okay, so daily would be 365. Okay. All right, and then this is 365 times 10, because that's the amount of years we're going for. So 0.06 divided by 365 plus 1 to the 365 or 3,650th power times 1,000. Okay, what about hourly? So we would need to think about how many hours are going to be in a day, which is 25. There's 365 days in a year. So I need to take 365 and multiply it by the amount of hours in each day, which is 8,760. Okay. And all right, so then what we can do is say this is 1,000. My 6% divided by 8760. 8760. 0. All right, because we're multiplying it by 10. Okay, 0.06 divided by 8760. Okay, really, really small number, and we're going to add 1 to it. Okay, then we're going to take that to the 87600 power and multiply by 1,000. I accidentally did 100 there, no big deal. Okay, you may have noticed that this price is, or this amount of money we're having is almost the exact same, but the cents have just increased. Okay, let's do minutes. So there's 8,760 hours in a day, and I multiply that by 60 to figure out the minutes. It's 525,600. Okay, and we're going to take our 6%. We're going to divide it by 525,600. We're going to raise this to the 5,256,000 power. Okay, and so all you can do is we're increasing the amount of times in a year. So we started by every 3 months, then every month, then compounding it every week, then compounding it every day, then compounding it every hour, and now we're compounding every single minute. Okay, so as we do that, 0.06 divided by 525,600 plus 1. Okay, so I get that. 0.06 divided by 525,600, we get this. Add 1 to it. Then we're going to have to take that to the 5,256,000 power, and then multiply it by 1,000. Okay. All right, so what we can look at here now is this concept of continuous growth. Okay, so if you think about how how like a plant grows or how you grow as a person in your height, you don't just start, if you do a height tree, you don't just start at, age 1, I am, I'm this tall. And then all of a sudden, you just, at age 2, you just wake up all of a sudden and you're this tall, right? There's growth in between age 1 and age 2, right? So when you're at 18 months, you're growing from one day to the next. You're growing. Growth is continuous, okay? Whereas here, there's no growth in our amount of money here in between each of these 4-month or 3-month periods, okay? So, at this amount only grows once every 3 months or 4 times in a year. This one only grows 12 times in a year. This one grows 52 times in a year. This goes 365, 8,750, 525,600 times in a year. Whereas continuous growth is more natural. It's like I said, like how a plant grows, like how a person grows. It's always growing. It never just jumps in height or in money, unlike this here. So what we're going to do is we are going to look at the formula for continuous growth, because continuous growth is what the natural base E is going to represent. Okay, so what is E? E is the base rate of growth shared by all continuously growing processes. Okay, so this right here is the key thing. Okay, E is the basic rate at which things grow naturally. Okay, so E lets you take simple growth rates where all change happens at all ends of a year and then find the impact of compounded continuous growth where every nanosecond, and actually faster than that because it's literally constantly growing, continuous growth, no jumps in our data at all. Okay, E shows up wherever systems grow exponentially and continuously, so things like population, radioactive decay, certain interest calculations, and more. Okay, E is not a random number. It represents the idea that all continually growing systems share a scaled version of a common rate. Okay, and E for us is going to be 2.718281828, blah, 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 blah. It's similar in how, like, pi, it's an irrational number, but it does represent something. It represents a ratio between radius and circumference. Okay, E represents the basic growth of naturally growing processes. Okay, so that's what E is. That's what it means. It's a naturally growing rate, and it gives us those. And so when things grow naturally, we will use that E. But some things to know about E that can be kind of helpful to you all is that E is just E's just a number. Right? I mean, we gave a decimal approximation above. It's just a number, even though it is a letter, it's E, it's representing a number, so it still will hold all the same properties that E would to begin with. So, for example, if I'm multiplying E to the third times E to the sixth, okay, if you know your rules of exponents, you know that I would keep my base E and add the exponents. 3 plus 6 is 9. Okay, so it holds all properties that any other property would hold. Okay, so if I have 16 times e to the fifth divided by 4 times e to the second, okay, well, I can split this up and take my 16 over 4 and multiply by e to the fifth over e to the second. 16 divided by 4 is 4. E to the fifth divided by e to the second is e to the third. So you get to treat it like any other number. Basically, as if it was a variable, you would be able to treat it. Okay, more exponent rules, right? If I have a power to a power, okay, you're going to multiply these exponents, okay? So in a situation here, even though we get 3 to the second times negative 8x, okay, 3 to the second is 9, okay? And I know we've actually talked about in previous problems about always have your negative exponents into positive ones. E ends up being one where it ends up being relatively acceptable to have negative exponents, so I would accept either of these. Okay, So pause the video, take a moment, see if you can apply some properties that we already know about numbers and just apply it to E. Okay, so I'm assuming that you've already tried these problems and you're just trying to see how you did. E to the 4th times e to the 7th is e to the 11th. Okay, 18 over 8 times e to the 11th over e to the 7th. So 18 over 8 is the same as 9 over 4. And then e to the 11th divided by e to the 7th is e to the 4th power. You would just subtract your exponents. Okay. And then here we would get 5 to the 3rd, and then e to the 12x. 12x because 4 times 3 is 12. Okay, and so this ends up being 125 times e to the 12x power. Okay, so far pretty simple. Okay, the big thing you need to know is e is just a number. Treat it as any other number, right? So if you need to combine like terms, you can combine like terms as long as it has another e attached with it. And the other thing that we kind of learned is that, you know, e is the base rate of naturally and continuously growing exponential properties. All right. Okay, so let's just get into some problems. Okay, so here's just some more interest problems that we were dealing with. Money often tends to be something that you all get along with pretty well. Okay, so we want to use E in a real life context. So the formula for continuously compounded interest is given by A times P to the E power, E to the power of R times T, where A is the amount, P is the principal, R is the rate, interest rate per year, and T is the time in years. Okay, so what we want to do is suppose that somebody deposits $50,000 compounded at 7% continuously. Okay, so at some point you are going to have to know the difference between when I use this formula and when I use that original formula that we used here. Okay, like this one here. Okay, so one thing you need to consider is, well, what does E mean, right? E is going to be used when it's continuous exponential growth. Okay, in this situation, we have continuous exponential growth. Okay, and so then we want to use this formula because that's the one that represents continuous. Okay, so A is the amount, which we don't know what that is. We're trying to find that. Okay, P is the principal. That's the original amount of money deposited, so that's going to be $50,000. Okay, R is the rate, which is 7%, which for us we need to know is going to be 0.07. That's written as a decimal. And then T is the time in years for us, which is 5. Okay, so we just basically got to use the formula. So A is equal to 50,000, okay, times E to the 0.07 times 5 power. Okay, so 0.07 times 5 is 0.35. Okay, and so then now all I have to do is figure out how can I use E. Okay, don't use that decimal approximation that was on the first page. Don't use that. Go ahead and just use the E button on your calculator. Okay, so if you're using a TI-83 or 84, really any of them or some emulator that's simple or similar to that. Okay, if you look here, you have ln, which is the natural log. We will be using that in future lessons. But this E is really what we're looking for, okay? So to get that, you're going to have to hit the second or the shift button and then this, okay? So let's go ahead and type the whole thing in. So we're going to have 50,000, okay? And then second ln will get you the E, E to the 0.35 power, okay? And it does give you parentheses for you to close with. Okay, so the amount of money I'm going to have is $70,953 when it's all said and done. That's if it's constantly, continuously growing in my account. $1.38. Okay. So if it's constantly growing in my account every nanosecond from when I put it in to when I'm looking at it 5 years later, it's growing, okay? That's the amount I'm going to have when it's done. As opposed to if it was compounded quarterly, it's going to go every 3 months, it's going to jump up. 3 months later, it's going to jump up. 3 months later, it's going to jump up. 3 months later, it's going to jump up. Here, it's not. It's going to be growing and growing and growing and growing continuously. Okay, how much money at the end of the term? Okay, so how much money is at the end of the term? Okay, at the end of the term is this money right here, $70,953.38. But how much money in interest was earned? So think about this right now based on the question that we have. Like, how can I figure out how much money and interest was just earned? How much money did I gain? Well, you want to look at what did you start with and what did you end with? We started with $50,000. We ended with $70,953. All you're going to have to do is take your $70,953.38 and subtract away your $50,000. Okay, take your end and subtract your starting amount. Okay, and when that's all said and done, you're going to find out that you made $20,953.38. That's how much was earned. Okay. So, now's a really good time for you to pause your video, take what you've learned in example 4, move on to letter D. Okay, so pause the video, try that one on your own, and then when you are done, check it with me. Okay, so I'm assuming that at this point you've already tried this one and you're trying to do letter D and you're here to check your work. So let's go ahead and do that right now. Okay, so you suppose that somebody has deposited $19,500. Okay, so somebody depositing an amount of money, that's going to be a principal amount. Okay, at 6% annual interest, so 6% is going to give me 0.06. And they're keeping it in that account for 3 years. Okay, how much is at the end of the term and how much was generated in interest? And we don't know the amount because that's what we're trying to find. Okay, so A is equal to my principal times E to the 0.06 times 3. So that means my amount is equal to 9,000 times E to the 0.18 power. Okay, so let's go ahead and type this in. So 19,500 times E. So E, again, is going to be second, and then ln. Second, ln. Okay, and that will give you the E that I have up on here, and 0.18 power. 23,345.74. Okay, so how much money is there at the end of the term? It's 23,300 or 345.74. How much was earned? Okay, put end of term. Okay, and then how much interest was earned? So my earned amount is going to be 23,345.74, and I'm going to take away 19,500. Okay, so 23,345.74 minus 19,500. Okay, so all I'm doing is typing that into the calculator. And it's going to be $3,845.74. Okay. And again, I knew to use E because it's compounded continuously. Okay, so you at some point you're going to have to identify, when am I using the original compound interest formula and when am I not? Okay, when are you not? When it's compounded continuously, when it's compounded in any other increment, quarterly, yearly, monthly, minutes, half year, you're going to use the original formula. Okay, so suppose that after 4 years of continuous compounded interest at the rate of 6%, an account has $54,000, $54,321 in it. What was the principal of the amount? So let's find the different key pieces. So we know it's taking 4 years. 4 years of compounded interest at a rate of 6%. We don't know what the principal is, but we do know the account has $54,321. Okay, so let's just set up this formula here. So we know that $54,321 is equal to the principal times E to the 0.06 times 4. All right, and so when I look at this here, I know that I can multiply 0.06 times 4, so 54,321 is equal to the principal times 0.24. Okay, and then again, this is going to come back to that very first couple things that we talked about. One, E is used when we are using naturally occurring continuous exponential growth or decay. Here, we have the continuous compounded interest. Okay, so continuously tells me I'm going to use this E formula. But also we talked about that E is just a number and that it operates as if it were just a number. So we have P times some number, right? E to some power is just a number. And we're trying to find what P is equal to. So what I can do is I just have an equation, and I can just take and I can divide by E to the 0.24 power. Okay, so we know that 54,321 divided by E to the 0.24 power is going to be equal to my principal. So let's actually find out what that principal is. So 54,321 divided by E to the 0.24. Okay, so here's what I'm looking at here. Again, I got the E by hitting second here, and then ln here. Okay, and then I'm just hitting enter and find out that it was about $42,730.41. Okay, so the principal here, $42,730.41. Okay, so notice that 5, in contrast to 4, although it has a lot of the same pieces, we're just starting in a different spot. In this particular problem, we have how much we ended with. We just don't know how much we put in exactly. So we have to do a little bit of work to find that, okay? As opposed to this one, we know how much we started with. I want to know what I'm going to end with the rate that I'm working at. And so then here we can just go ahead and say that, plug in and use the formula. Here we're going to plug in, but then we have to solve for the formula. Otherwise, it's virtually the same thing. Okay, pause the video, move on to letter E, and go ahead and give that one a shot, and then check it with my work here in a moment. Okay, so I'm assuming that you've already done this one, and you're here to check your work. Okay, so suppose that after 4 years of continuously compounded interest at a rate of 8%, okay, at a rate of 8%, an account has $54,321.54321 in it, and I want to know what the principal is. Okay, so let's go ahead and use our formula. We know that A, or 54,321, is going to be equal to the principal times e to the 0.08 times 4 power. Okay, so this means 54,321 is equal to the principal times e to the 0.32 power. Okay, and then if I want the principal by itself, I'm going to have to divide by 0.32. Okay, and so I have to take 54,321, I'm going to divide it by e to the 0.32 power. All right, and I get $39,445.14. Okay, so that means when it's all said and done, I know that this is the amount. This is all equal to the principal, and then this amount, oops. I know that this amount is equal to the principal, and then that amount, it happens to be $39,445.14. Okay, that's how much we started with. Okay, overall, some things that you should be able to do, leaving this one, is identify growth situations as either continuously or non-continuous. Okay, and if it is continuous, you're using E. If it's not continuous, you're not using E. Okay, furthermore, you're also should be able to simplify some basic expressions, okay, that have E in it, okay, because E is just a number. Otherwise, you can move on to the homework for 8.2, and when we're done with that, we can move on to 8.3. Have a good day.